In our last lesson, we looked at the connection between wavelength and frequency. Today, we'd like to apply it specifically to sound waves. So we learned that waves are created with a certain frequency. That is determined by the source that is actually creating the wave. So when I hit the tuning fork vibrates with a set frequency. As the waves travel outward, there is a certain distance between the wave fronts. The connection between them is higher frequency makes the wavelength smaller. A higher speed makes the wavelength bigger. We put it all together and we had a formula that looked like this. Wavelength equals the speed of the wave divided by the frequency of the wave. Today we'd like to talk about sound, and we'd like to look at frequencies and wavelengths. Sometimes the frequency is the more important thing, and sometimes the wavelength is the more important thing. So determined by what we're looking at determines whether or not we want frequency or wavelength, and the formula that we learned yesterday will help us translate from one to the other. So first of all, remember that the frequency of a sound wave tells you its pitch. So the green wave has a much higher frequency, it would be a much higher pitch. Oftentimes you'll see the frequency of sound laid out in such a way that you can see how many high frequency waves the sound is composed of and how much low frequency sound that the combined sound is composed of. So this is called an equalizer, and if you're listening to music, you'll see these bars going up and down depending on what's happening. When there's a lot of drums, you might see a lot of low frequency sounds. When you have things like a piccolo, you might see a lot of high frequency sounds. So the low frequency, the bass is down here. The high frequency treble is over on the right. You'll notice that the highest frequency on this equalizer is 20,000 hertz. And you'll notice the lowest frequency is 20 hertz. The reason why they pick these as their starting and ending points is because that is the range of human hearing. On average, some humans can hear different frequencies than others, but in general, the low end is usually started at 20 and the high end ends at 20,000. Okay, here is a chart showing you a bunch of different animals. And again, with humans, you can see we start around 20 and we end around 20,000. Realize that as your body ages, this range of hearing tends to contract. Okay? You can also do damage to your hearing by listening to too much loud music or sounds, and that will cause it to contract faster. You'll notice there are some animals like elephants that can hear frequencies lower than what humans can hear. And you can see there are some animals like dolphins and whales that can hear frequencies higher than what humans can hear. Okay? So the range of frequencies is different for different species. This equalizer is for humans. If dolphins were creating an equalizer, they would show a different range of frequencies. Okay, there's names for sounds that humans can't hear. So infrasound refers to sound waves with a frequency too low to be heard by human ears. Infrasound. It is the kind of sound waves that might be created by a large explosion, okay, a nuclear blast, an earthquake. So these are detectors that are listening for infrasound through the surface of the earth, okay, and they would help scientists be able to pinpoint when events that create infrasound actually occur. So great for spying on other countries. Okay, we also use ultrasound way more commonly, and ultrasound has two uses we want to talk about today. One is in the medical field, and one is in the automotive field. So on the medical field, you have probably heard of ultrasounds before. Some of you may have actually had to go in for ultrasounds. So you can do an ultrasound, let's say, of your carotid artery, and they can see whether or not the blood is flowing properly through the artery. They send the sound wave in, it bounces off the artery, and is picked up by the detector. That then is turned into a picture using computers based on how the waves reflect off of the artery. And the smaller the wavelength, the more detail that they can actually see. So with our formula, if we want a small wavelength, we want a very large frequency. So the higher the frequency, the more detail we can see. So this time, the important thing is the wavelength we're using. Smaller wavelengths give us more detailed pictures. With cars, you'll notice they have a transmitter that sends out ultrasound. It bounces off of an object and is picked up by the receiver. The computer would then measure how much time it took the wave to leave and return, and it could work out how far away that object was from your car. So you might have these on the back of the car, the front of the car, the side of the car, and it will be able to let you know how close you are to different obstacles. Okay, when we talk frequencies of sound, there are a few special frequencies. So for instance, this tuning fork has a frequency of 320 hertz, which gives it a frequency often referred to as an E. The note is called an E. Some of the more important notes are designated with Cs, and the C note is the one that is right next to the two black keys. The two sharps and flats that are here, the white key right next to it is designated with C. There's a lot of Cs on a piano. The one right in the middle of the piano is known as middle C. And the value for C and all the other notes next to it are given to you right here. So C is 256 hertz. E is 320, like I said just a moment ago. When I strike this tuning fork, it'll oscillate 320 times per second, and that is designated as an E. Okay, you'll notice that when we get to the next C, I put that one in the wrong spot. You'll see when we get to the next C, it's got a frequency of 512. And you'll start to notice that these numbers are not random. That when you go from one C to the other C, your frequency goes up by 2 times. That's called 1 octave. Okay, so every time you go up an octave, you double the frequency. So if I went to the next E, it would be 640 hertz. When you go down an octave, you would cut your frequency in half. Now realize these numbers that you see on this piano are not the important thing. To make it musical, it's the ratio of one number to another. Like for an octave, we saw the ratio was 2 to 1. So what makes it C and D and D and E are the ratio between these numbers. So sometimes you'll see pianos with a different set of numbers, and that's fine, so long as the ratios are the same as they were for our ideal scientific piano. So here we have a piano based off of A being 440, and you'll see all the numbers are a little bit different, but you will see the exact same ratio between a D and a C. You'll see the exact same ratio between a C and a C. All right? So it's ratios between frequencies that make them sound nice. I have 3 math problems I'd like you to try. The first one deals with the range of wavelengths you get when you go from one note to another. And I would like you to start with middle C, and I'd like you to end with the B value, the second B following middle C. So not this B, but go all the way to that B. It's going to give you a temperature of 19 degrees. You're going to turn that into a speed of sound. You're then going to use that in here, and you're going to solve for your different wavelengths. Do it once for C, which is 256, and do it once for the B key that is 1 octave above 480. All right? Why do we want to know the wavelength of these sounds? Well, if we were designing a building that was going to be designed for those sounds, maybe an opera hall or a music hall, we want to know the size of the waves so we could design the material for the walls that are either going to absorb wavelengths we don't want or reflect the wavelengths that we do want. Okay? So the acoustics of the hall is going to be based on the wavelengths that you want to amplify, the ones you want to accentuate, let's say. The next one I'd like you to try is for an ultrasound machine. So once again, you're going to be using this formula. The speed is given to you. You're going to go from 2 megahertz to 18 megahertz. And you should find 18 megahertz producing smaller waves, which will give us a better image. The final one I'd like you to try is for an earthquake. And this time I tell you the period. So remember that period and frequency are reciprocals of each other. So before you can use our new formula, you have to use the old formula to turn period in the frequency. I know I went quick. I hope you understand how wavelength and frequency are connected for sound waves, and you can work through all of these problems. If you have any questions, see me during the Macaulay one time.